Can I ask
Do you
you
want
a question? Because I have a question about stresses that came up as we were doing this. So we're dealing. I guess we just want to start our presentation.
go ahead and
Oh,
ask,
fine.
and then we'll.
Okay,
I was
so-
going to start with these guys, but.
Oh, never mind. Well, yeah. So you have an iceberg or something. As you go deeper, the pressure, which is the stress, increases. So how do we?
Well, pressure is not necessarily identical to stress,
Okay.
but
well,
it does play a role in the stress.
But like the stresses are stronger the deeper you go.
The
I
pressure
think.
is stronger the deeper you go.
Doesn't that mean the stress?
So that part of the stress, yes, you will have
Okay,
an
yeah.
increase in the pressure
So-
part of stress.
So how does the tensor? Do you just put the equation like for depth in the tensor?
So yeah, so the stress tensor. Remember the stress tensor and it's the coordinate system we know it in. That exists at a point. It is the stress at that point.
Yeah.
So if you have a changing stress in your body, it might be the same everywhere, but it also might depend on, this is why we use 1, 2, and 3 for our tensor coordinates, but we might use X, Y, and Z to look at distributions within a whole body if we
Yeah.
need to have different coordinate systems. Sometimes you can have them all be the same, but so
The stress tensor is a function.
the stress tensor can be a function of space,
Okay.
which you might be able to write it out then by having components of the stress as a function of X or Y or whatever your spatial dimensions are. Does that make sense?
Okay.
Yeah.
Yeah.
Because this, and you'll see this when it comes in, both of these have. So why don't you guys go ahead and explain what your problem was, what the question was, and how you guys got started on it, and I'll move this into the.
So we have a box, apparently, and it has the density,
Well, it's a plate. It's a
it's-
thick, like a lithospheric plate.
and we are asked to find the coordinate system. So we will go with one.
Oh,
Oh,
sorry. I just wanted to finish. I forgot to
Sorry.
put. So this is the lithospheric plate, and what are the arrows on the side? I forgot to put the magnitude of those.
Oh, it's 10,
10
megapascals.
megapascals.
So lithospheric plate that's undergoing extension, 10 megapascals in one direction, and has gravity acting on it in the other direction.
Are we looking at the plate from on top? I'm confused.
This is a cross section of the plate.
Oh, of course.
Yeah.
Thickness is H.
So we are asked to find the coordinate system. So we assume it is 1 and 2 coordinate system with. So it is like the same all the way through the third axis. So we just make a cross section out of it. And it also says that we have to assume the length of the plate is very large compared to the height of the plate.
And why do you think I told you to assume that? I told those guys the same thing.
So that when we integrate, when we find the stress tensor on the B and A, it is easier to assume that it is long, so we don't have to deal with the height because the L is really long.
Well, you'll still have to deal with the height, but what specifically don't you have to deal with?
The gravitational force will be the same. Well,
Yeah,
almost A and B.
between the point
No,
A
I
and
want
B.
you to keep the gravitational force. It still is a finite thickness, but there's something else that happens. What if L and H were equal? A and B might still be the same, but what if I didn't put, what would happen as we got closer to this edge?
in the ideal world, yes, but
No, we don't live in an ideal world.
okay, so it's not.
Which is why we say that this cliff is 1,000,000 miles away, because we don't want to deal with the cliff. So I mean, you could say, yes, we're talking about an ideal world, but the way we define ideal, we have to state explicitly what all of our assumptions are in that ideal world. And so in this case, we're going to assume that L is big enough that our cliffs are far away, and we could move A around even a little bit spatially, and as long as
Along
the
the-
cliffs are far enough away, then we don't have to deal with the cliffs. There is going to be other situations where I'll tell you that L is much bigger than H, and that might mean that we can assume all the properties are the same between A and B. Like, it'd be easy to say the material properties are the same, or we might integrate and just assume we're assuming those are the same point. But in this case, I do want you to think about A and B as being gravitationally different. It's just the cliffs are far away.
Is there a term for that assumption? Or is it just
Which one?
like
There's-
if you take the like L much smaller than or much larger than H?
If you're thinking about it in terms of the A and B being basically thinking of it as a whole column of the same,
Mm-hmm. Yeah.
there's a couple of different terms. That viscous thin film that
Okay,
you
I
guys
think that's
remember
probably
from
what I'm
the
thinking of.
from that paper we read. So thinking of it as a thin sheet,
Yeah. Okay.
or a depth integrated.
think it
Sometimes
was that
we'll think
paper.
about it as just the depth integrated system, but we're not quite to that yet. We will get to some depth integrated or viscous thin sheet kind of assumptions. It's a similar assumption, but in this case it has a slightly different purpose. But my point is that you have to be very careful in stating what you mean by the ideal world for your particular case. So what assumptions you're making, and I will harp on this a lot. Like, even if it seems like a simple and obvious assumption, I still want you to write it down. Because it's not always as obvious and clear as you might think, and there might be two relatively similar obvious and clear assumptions, and your reader in your paper in the future might be like, well, did she assume this or did she assume that? They both would be reasonable in this situation, and if you don't state it, you can't just assume that your reader will know. So, but good, okay, keep going.
And so the stress tensor for this case would be
Did you decide on your principal directions? I'm
Oh.
not sure that I heard that.
well, not yet. Yes.
Okay.
So the principal direction is happening on the 1 1. So it's 0 0 0 0
That's ignoring gravity.
0. If we ignore the gravity on point A and point B.
Okay, so this is ignoring gravity. And what are your principal directions?
Because it will deal with the 3 invariants, and we didn't have time to calculate that. 'Cause-
Can you guess? What do you
Yes.
instinctively think the 3 principal directions are going to be?
It would be like 1 and 2.
So yeah, 1 is going to be 1, and 2, because that's the 10 megapascals are in the 1 direction. And is there any shear? So remember that the principal directions are that coordinate system where there is no shear. There's only normal forces, normal stresses.
I think it will be the same because even it doesn't have shear forces, so we don't have to rotate or change the
Right. So I
The
gave it
tensor.
to you. I drew it in what is probably the most likely principal coordinate system. So the 1 direction is a principal direction, and then the 2 is the direction of gravity, so that's most likely going to be another one. Is the 3 direction a third principal coordinate system? A third principal direction in this case? Does it have 3 unique principal directions?
Yes.
Why?
Well,
You're
you
right.
Give a
You're
value,
right. I just want
it's
you to say
zero
that.
for now for this description.
No, I'm not asking about the value. I just want to know why you think there's 3.
Because it's we live in a 3-dimensional world.
Well, we do live in a three-dimensional world, but
No.
yeah. I gave you that P, the 10 megapascals is only in the one direction. So it's not symmetric in this third dimension. So I was
gonna say it was a 2D image, and there wasn't anything in the image you drew to indicate a third dimension. I was gonna say there's only two.
But we live in a three-dimensional world.
fair
So
enough.
everything I give you, assume
Okay.
3 dimensions.
Okay.
Always, because we live in a three-dimensional world. But I did not give you a stress in the third dimension.
So it's 0, but it does.
So it's 0. How do you know it's 0?
I assume if you didn't give it to me, it's 0.
That's not a good assumption to make,
Okay.
unless you have a reason that you can state that it's, because it could be the two options for that third dimension are either that the stress is 0, which means that it could be, if we stretch it this way, it could be thinning
Mm-hmm.
to conserve the volume, if
Mhm.
we, depending on the properties.
Mm-hmm.
Or I could tell you that it's not thickening or thinning in that direction,
Mm-hmm.
which means there might be stress keeping it from moving. So just assuming that a stress is 0 because I don't give it to you is not necessarily a good assumption to make.
But is
So you have
that
to be very careful about
is that the assumption you'd make if you want to move from 3-dimensional to 2-dimensional world?
No,
Okay.
because of that exact thing. Like I could tell you, you can either do 2 dimensions by assuming there's 0 strain in that dimension,
Okay.
or assuming there's 0 stress, and those are very different solutions.
I see.
So you have to decide one way or the other.
Okay.
And we actually always are conscious that there is a third dimension. Like we never simplify things to a 2-dimensional
Okay.
world because
Fair
of
enough.
that there are alternative. So if you don't know what's going on in that 3-dimensional world, in the third dimension, what I would start with is saying, let's put a question mark there. Because we don't know yet what it is. And the best part is that to answer the question that we're after, it may not matter what that is. Sometimes it will matter, but other times it might not matter. So, okay, good. So we have, this is assuming there's no gravity. Now, but I gave you gravity, so now what's the difference?
There's gravity, so it's happening on the 2-2.
Mm-hmm.
Yeah. So can we call it just G for gravity? Oh well, it's sorry.
That's an acceleration, not a stress. And maybe you guys also have to think about gravity, so maybe you could jump in and help, or
well, we assume that L is really long, right? So we don't.
Mm-hmm.
what's the pressure at depth in a swimming pool?
Rho times gravity times height.
Right.
Density.
So that's a pressure. And how does a pressure look in terms of a stress tensor?
Oh.
So you have this nice one that assumes no gravity. So why don't we just write a new one that's ignoring the 10 but assuming there's gravity in there, just to, and we want to do this for point A and for point B.
So we'll have 0. So we put the gravity force divided by the area for that 2-2. Is that
So rho GH, is that a force or is that a
that's
pressure?
it's
Rho
I think
GH.
it's force.
There's a pressure.
What does a pressure look like in stress tensor?
It's
It's one of your elements. It's one of your
Dimensions.
One.
Or
So if I'm sitting in the middle of a swimming pool
Oh,
and
it's
I'm
all
under
directions.
stress,
Rho
it's in
IJ.
all directions.
yeah. That's
So gravity, rho GH, is
Yeah.
a pressure, and it's acting in all 3 directions as normal forces. So what does that stress tensor look like?
So 1, 1, 2, 2, and 3, 3.
So draw it there as just the
Just G.
gravity.
So
stress
just
tensor.
like
Forget the 10 for now.
like, can I call it G for that point?
Rho GH
Okay.
is the pressure.
Sorry. Yeah.
So the magnitude of the pressure is rho GH. And what is H?
It's the height from the box to from that particular plate to
Right.
the surface.
So we now have, we go back and put that 0 in there. This is just due to the regional 10 megapascal stress.
Yep.
Rho GH is our pressure. And so the net, what's the net stress at B then? I mean, sorry, at A.
10 plus rho GH. Or no.
Would H be 0 at point A?
H is 0 at point
Okay.
So it's 0
So it's
all
0.
over.
A. It's 0. And what is it at B?
It's rho GH.
So this is where you were asking about writing it
Yeah.
as a function of Z, which you can do. So we have an overall stress in this system, regional extension in this system, plus the overburden stress, pressure, if that's what you want to call it, from structural geology. And they do combine together to give you an overall stress for that particular location. So the stress is different at A and at B. What do we know about the shear stresses? So you put zeros in there, but I don't know why.
I think since all the sides of that box, they get all the rho GH, right? So basically, it can also be the shear forces on the bottom and on the top. Or, every side has the rho GH.
Well, the rho G pressure is a normal force.
It's normal, even though it is like I don't know, like on the bottom of the box is touching.
Well, you
Can we assume that?
you wrote this right. This is pressure is just the normal forces.
Okay.
So if you're just thinking about pressure, there's no shear forces in there.
Okay.
So, I mean, it's probably right. I would say that we may not know. We don't know what's happening in this third dimension, so we have to be careful about putting zeros in here. But we do know what's happening in the one direction and the two direction. So I think it's right that there's zeros here. I just want to emphasize that you have to acknowledge what your assumption is there, that there are no, there's nothing providing a shear in this system.
In the one,
Right.
two directions, but the third direction we don't have like enough information to assume that.
Right.
there's
So
no
what if I
shear
told
forces.
you there was a mantle flow along the bottom of this?
Well,
Would you then be able to make that assumption that there's zero shear? Not anymore, no. So you could have a shear being applied to the system that you'd have to take into account. But right now, except for the third dimension, which I didn't tell you anything about, I basically told you that there's no shear. There's just this extension and then gravity. So, does that make sense? Their problem has some similarities, so hopefully it'll become a little bit, well, there was one more.
The fault part.
The fault part. I guess really quickly, what do you think based on what we just did and the difference between the stress tensor at A and B, do you think there's a difference in how that fault might behave at the two? The question is if there were a fault with a 45-degree dip at A or at B, would the chances of them slipping be different at those two, or?
At B, there would be a component of the gravitational force acting along the fault.
Right.
But at A, there wouldn't be.
At A, there's not, right. So in A, it's pretty much pure extension, which means it's probably more likely to slip than at B, where it's got this extra overburden pressure on it. Yep, so we could go back and calculate the traction on that fault at both A and B and see that in a more mathematical way. Cool. Okay, so just do that. And then you can draw your picture, which hopefully this one should go, now that we've talked about some of these concepts, it should be a little. So this one is a floating iceberg rather than a lithospheric plate.
Oh, you even gave us, I didn't actually see the numbers when we did this. Oops.
Oh yeah, if you do little dots
Sorry.
and circles, it gets confused, and it thinks you want to copy and paste and cut and stuff. So
It's also hard to aim those things.
it is, yeah. You
Okay,
got it.
so
There we
there's 3 points throughout. Yeah. So we were sorry. This is supposed to be a C.
That's all right.
Anyway, still not very good. Yeah, our problemast wanted us to choose a coordinate system for this, and so we have an iceberg sitting in the water. Its length is a lot longer, so I guess. And so it's a lot longer than it is tall. Pardon my handwriting on this thing as well. We also have some densities. So we have a density of water. Actually, I'll just say we have a constant density.
Yeah.
And so these bodies are uniform, and the density is not changing
Good.
throughout any of it. Our cardinal, or do you want to talk about anything?
No, because now
What's
I'm
your
even more
coordinate
confused
system?
than when we started working on this one. So
Well, anyway, the
Um.
principal directions were chosen to be just 1, 2, and 3. It doesn't.
Okay.
For a pressure is kind of applied uniformly. I thought it might be nice to put 1 going in the up and down direction, because the only difference that we're looking at is what's the difference in the up and down direction of like how high the iceberg is sitting versus the water level and stuff.
So, do you have
Um,
3 distinct principal directions like they did, or?
So I mean, they'd be just the place that
But
defines any
the-
system.
But what if I
Because
started?
gravity doesn't equal point force. So I don't know.
If I started, the one is definitely
Yeah,
a
so there's-
system, but
there's-
if I started spinning it around this way, is there any
No,
preferred?
no, not at all.
No. So there's
Maybe
only
two. Okay.
distinct routes in this system. So there is no principal direction. And all directions in this plane are principal.
Okay.
So you might choose one to work in, but
Okay.
because of the symmetry,
Yeah.
you can't define separate principal directions in that.
Okay. I see.
So you just have to be. I mean, it's you have to pick something,
Yeah.
but it's good to acknowledge that there is that symmetry in the system. So
Does that mean there's only one principal direction or two?
If you're using
I think there are two, because only one principal direction would be a pressure type where it's the same in all
yeah,
directions.
Okay.
Yeah, it does. The as we'll see from the tensor, it will vary as you go in one direction. But well, I mean, everything varies in that direction. So, and that isn't related to the tensor. Or I mean, it is, but it's not.
It's
It's not related to the orientation. Yeah, and so our questions, one was, what is this depth d? How low into the water does the ice sink for some iceberg of height h? And then also, what's the stress tensor? And so to solve this out, we noticed that, that the pressure of water is equal to the pressure of ice. And so the pressure of water.
where is that? Everywhere or?
So we were looking at the bottom.
Okay, at the bottom.
Sorry, at the bottom of it. I should. Because otherwise it wouldn't. The pressures will equalize. The forces will be equal, and it's done in motion, and so then rho water g times d equal to rho ice g times h, and so we can move this around and get that d is then equal to and then just going by the pressure of ice and pressure of water, this is 9/10 h.
Right, because the density of ice is 900 and the density of water is 1,000 kilograms per. Pretty close.
And so we also and that the main, or I mean the only stresses acting in this situation are the pressure, and so I'm gonna just define a new. I'm gonna say there's an h that's just a depth underwater, and so we were looking at what the tensor is gonna be. I'm done. Maybe put this somewhere else.
You can. There you go.
You wanna do this?
Nope.
Well, actually, it's gonna be. gonna be. I'd have to define it for ice. Let me just use water. I'll do it here, but though actually, I realize that it's not going to be H. It's going to be H plus. Is what the term for H should be. Now that I think about it, but
H plus. So might be simpler because right now you've defined this as the water surface, but we're looking at
yeah.
H up there. So this is where you defined the coordinate system, but you didn't put an origin in here.
Yeah.
And it might be simplest to just choose an origin. And in this case, I would probably either choose C or A as my origin, and then reference the weight rho of the ice times G times the distance from that top, which we define. It might be H minus Z or something, depending on where your origin is. If your origin is down here,
Yeah.
Z is there, H is there, it's that difference. If your origin is at the top, you can do a negative Z.
Yeah.
Does
I
that make sense?
realized my.
So you have to figure out where you want your origin to be to figure out what that should be. But this then applies along this column from A, B, C. When you're in the water, you're going to have a different stress. So one of the reasons I said that these cliffs are far away, but generally, so this stress, say this stress halfway,
Is there a pointer thing I can?
so the stress at the very top here, A, is what?
Oh, at the very top, it's going to be 0. Well,
Zero.
in.
It's got, and this is also, it has a free surface, so it's exposed to the air.
Yeah.
So we'll have, it's a free surface condition. What if we came down just to right there?
Yeah, there's some weight above the ice.
So there's a little bit
So-
there, but what's the stress here on the very top?
0.
0. So now we have a stress that's higher there in the ice because there's just air over here. So even though we put this cliff as far away, ultimately this iceberg is going to want to expand out unless we actually give it a force on the side. Right now, we're not holding it in place. There's just air there. But even if that's far away, there's still a net gravitational potential energy because it's sticking up above the water. So if we were to fix those boundaries far away and say that it can't expand, then we would have something that would be holding that ice above the water line. But as it is, we only have the water holding it on the sides. Even if those sides are far away, there's still only the water holding it on those sides, which means that it really can expand in those directions because the water isn't enough to actually hold it back, to keep it elevated above the water surface. So it's enough to hold it to hold it mostly, but there's still a net gravitational potential energy because the middle is higher than the sides. So you can figure out, if we were to also estimate the pressure distribution in the water, we can still forget about the funky stuff that's probably going on at the cliff. But if we compare what's happening in the water column with what's happening in the ice column, ignoring messiness at the cliff itself, we'll see that there's an imbalance of the stresses at those 2 points. Even if they're far away, there's still an imbalance between those 2 stresses. Those imbalances of the stresses would result in a stress that ends up driving extension, and that's called it's sometimes people call it the differential stress, but it's really the deviatoric stress. And so you can estimate how much, given the material properties, if you calculate the stress, you can figure out what that net extension is horizontally. So this case, what you've drawn here is really just considering gravity. It's assuming that there's actually a wall here that's truly holding up the whole iceberg, not allowing for that gravitational stress. So one of your last homework problem is to think about, well, if this is really just the gravity, what else do we need to know comparing these 2 sides, or these two environments, to figure out what that gravitational extension might be? And again, this ignores messiness at the cliff, because you're always going to have messiness at cliffs like that, or boundaries like that. But if you look at just that imbalance, because one is higher than the other, even though the weights are the same, so the pressure at the bottom is still the same. So the integrated mass in each column is the same, but the stress is distributed differently, which results in this imbalance. So it's the same total mass on each side, it's just distributed differently.
Yeah, I also would imagine that there might be some, like a little bit of it might melt in some way around here, and it kind of might come out a little bit, and then you get a bit of a shear, because then you have a shear going in that way. I mean, no,
Yeah,
obviously it's
you
really
get really-
long, so that's not like going to affect it, because it's
Right, you can get all
it's
sorts of
much longer
funky
than
stuff
each.
happening at that cliff boundary. They're messy boundaries that you need to find an element model to solve. Okay, let's do the last one, and then, because this is another.
Sure.
This one is a little bit of a different concept that comes back to our idea of, well, what is a continuum?
So we have repeating layers of sand and clay. They've got a particular thickness. We have rainfall from the top and water pressure from the left. The first question was to choose a coordinate system, and so I went with something like this, where so I did XCY. So x1, x3, x2. The second question is continuum versus discrete. What does it mean to treat this as a continuum? We decided that it would be discrete continua, because each layer itself you're treating as continuum. It's going to have constant or continuously varying physical properties like density and permeability. But at the border you have a sharp jump and a very sharp change, which breaks the continuum. So there you have to treat it as discrete objects, discrete layers.
But what if we zoom way out?
If we zoom way out,
And there's a bunch of tiny, they become a bunch of tiny layers.
Then it would be more
oh,
continuum. Yeah, we just zoom back in.
You just zoom back in.
so if we zoom way out and they're really thin layers, compared to the scale that we're worried about, we can give them just bulk properties and treat them as a continuum.
Especially since these are like alternating sand clay layers, we can sort of, I don't want to say average it out, but we could.
Well,
if
how
you're
would
looking
you,
at
how would
the-
you average it? What would that mean in terms of?
I mean, I guess you're averaging their permeability in this. Well, I guess we're looking at permeability.
Well,
this
let's start
case.
with, before we jump straight into permeability, what properties would you need to, what would we need to be averaged out?
The density.
We need to-
So the density maybe, yeah, because they've got different densities,
And permeability.
and the permeability,
And
and
the
then what about the
thickness.
geometry? The thickness.
uh,
Right, so is it gonna be, so if we had 20 layers, each with a thickness of 1 alternating, versus 10 layers, each with a thickness of 2 alternating, from your zoomed out perspective, is there gonna be a big difference in their ability?
No.
What did you say before? The first one?
20 layers with a thickness of 1
Uh-huh.
versus 10 layers
Of
with a thickness
alternating.
of 2, and they're all alternating?
No.
Is there going to be a
not
difference?
really.
No. So you could write it as kind of the total amount of sand versus clay
yeah.
times a certain percentage of the thickness, kind of a thing.
I'm not sure if you made that point. So, if you look at the bulk properties, do you actually care if it's alternating or not?
Right.
It's just
So
looking at there's
You're just
even though they're, like,
summing
so if you had
layers.
one giant clay layer and one giant sand layer, would you end up getting different
I think
results than having it layered?
for bulk properties.
For the permeability specifically.
yeah,
If you're looking at a
clay.
bulk, it's small compared to your scale, no. But if you were worried about
If
the
you zoomed
scale,
in.
then
Yeah. Yeah, no, it's
Yeah, that
exactly
clay
right.
layer's not going to get.
So if you zoom in and you are worried about, and you might have stuff going on, like maybe it's maybe you have more groundwater at this level than at this level, so you do need to worry about differences in the layers. Then yes, when you're zoomed in, you're going to have to think about these as a little more discrete layers. But if we zoom out a bit, and if we assume that your groundwater flow is uniform in this direction, then even if we're relatively zoomed in, the net result might not matter that much if we have one giant sand layer and one giant clay layer. If we're assuming that the pressure that's driving this groundwater flow is pretty uniform. Does that make
It's
sense?
true, yeah, because even if it's like broken up in layers like this, and water does not travel through clay
Exactly.
very well or at all, and so even like this, all the water is going to go through the sand. Even if it were in big bulk or big chunks, it's all going to go through the sand. So it wouldn't make a difference if you just say we have a percentage of sand, percentage of clay. Doesn't matter where it's at in matrix here. It's
In the horizontal.
in the
direction.
horizontal, yeah.
Right,
So of course it's
so-
going to make a difference in the
So it'll
vertical
make a
because
difference in the- So, how many of you guys have good geology backgrounds? We're on the right track though. Sand is very permeable. Water
Yes.
flows through sand pretty easily. Clay is really hard to get water through. So just looking at this, is it gonna be easier? Is it gonna be easier to move water horizontally in this system than
Yes.
vertically?
yes,
Yeah.
very much
Because
so.
horizontally, it can cheat and go through the sand as much as it wants.
I pressed a button.
Can you guys see that? So let me draw this, because this is, I like this problem because it just makes you think a little differently about, so here are layers, sand, clay, sand, sand. And in this horizontal direction, it's one pressure being applied, but that, I think he uses a V, but it's the volumetric flow rate, so it's the volume per time. is equal to the volume going through the sand and the volume going through the clay. And each one has the same dp, oops. So P1, P2, P1, P2, the same pressure is being applied to every layer. But in the end, the total that we get out when we think about these bulk properties is the volume in each layer adds up.
So it's,
Oh,
it's
yeah.
asking to add a trig function, so no matter what direction you go, if you have full flow, if you have a trig component to each volume of clay and volume of sand, then you can describe independently where the flow pressure is coming from.
If you, yeah, once you have this permeability tensor, yes, you could then rotate your axis and look at flow coming diagonally through the system if you wanted to. But so this is the horizontal. In the vertical, we still apply a P1 and a P2 over the whole thing, but it's the volume, the volumetric flow rate has to be the same in all layers. Because what goes in at the top has to come out at the bottom. That, unfortunately, I went off the page there. What goes in at the top has to come out at the bottom. So you have to be transmitting that all the way through, which means that when it's going through the sand, it's going to have less of a pressure. So we actually are going to add up. So we actually have P1.1, P1.2, P1.3, P1.4. At each boundary, you could, if you went in to measure the pressure, your dp dx total would be the sum of the change in pressure over the clay layers plus the change in pressure over the sand layers. So the volume is the same, but the pressure then is divided up between the layers. So the math is a little bit different, and it's the same series versus parallel that you guys have been thinking about with the other stuff. But the math is a little bit different, but given the pieces in there and knowing your percentage of sand versus percentage of clay, you can zoom out and figure out this one was your K11 component, right? No. That was your K33, which equals the K22. This one is your K11 component. So there's a little bit of a different math to get there, but once you have that equation, that's sort of basically it's an averaging of the material, of the permeability properties, but you can't average them the same in both directions. But then you'll end up with some K11, K22, K22, since those are equal.
Why were 3, 3, and 2, 2 equal?
Because they're layers this way.
I thought K1
Yeah,
was
that's
the
not
layer.
the coordinate system that they.
Oh,
One
okay,
and
one
two-
is one and two are the layers.
Are the layer, 3 is the vertical.
Okay, sorry
I
about
think,
that.
isn't it?
Yeah.
Okay.
Just to make sure I was
K22
understanding.
and 3, nope, 3, 3.
Okay.
Then we can say that the volumetric flow rate is the permeability tensor times 1 over the viscosity times dp I dx j. So now you could, we're zoomed out a bit, so we've basically created a bulk permeability for this material that has these properties. And now we could apply any pressure to it and come up with the flow in that direction. and we should come out with, if we do the horizontal pressure, we should get the horizontal velocity, flux that we created. Does that make sense? I hope that, we spent a little longer on that, but I sort of hope that sort of brought together a lot of these ideas on Unit 1. Any last questions? We have a
So if we assume that the water doesn't get absorbed by the sand, just curious.
We're assuming that everything that goes in must come out,
Okay.
which is a great transition to Unit 2. Actually. So, normally I do try to give us a break halfway through, and I forgot to today. So if you ever want to take a break halfway through, just say, "Hey, Erin, can we take a break?" If I get distracted. Okay, we only have 15 minutes left. Anybody desperately needs to take a break now, then that would be great. You can do stand-up 7-minute stretch, 17-minute stretch. So what Joshua just brought up is, well, what if stuff got stuck in the sand and then the whole system went out? And this is where we have to make some assumptions about conservation of mass and the flow and what we're doing and what our boundaries are. And so Unit 2 is really jumping now to conservation of mass and conservation of momentum. So how do we really start to think about these questions that we want to start to answer? And the general way that any geophysics problem usually ends up being answered is, the first thing you have to do is decide if it's conservation of energy, conservation of mass, or conservation of momentum that's going to be useful. And then what are your material properties, or whatever, if it's a deformation, then you're going to have like viscosities and that stuff. In this case, we have permeabilities. What are the densities? Are they constant? You're going to make a bunch of assumptions with that, and then come out the other end with figuring out what you want to know. So the details, of course, come down to what the answer is. What the question was, not the answer. What the question is, what direction you need to go with the system. But basically, we're almost always going to be applying one of the conservation laws. We're almost always going to have some set of material properties. And that as a whole really sets up the whole system. You really don't need to know that much more. But you have to start thinking through assumptions, which is what we were just talking about today, like listing all of the assumptions you want to make. And you need to define your coordinate system, you need to define the geometry, what you're thinking about, whether you want to make that viscous thin sheet assumption in a situation, or if you want to actually acknowledge that there's stuff changing with depth in an important way. But a lot of our problems are going to follow that same pattern. And so this next unit really is diving into what are the conservation of mass and conservation of momentum. You guys probably all learned in your high school or intro physics classes the basics of conservation of mass and conservation of momentum, and conservation of energy. We talk about those a lot. It's really nice. There's really one basic equation. We actually can think about conservation of anything as being our simplest, most basic equation. And the conservation of anything means change in anything, which I'm calling phi, as a function of time, which if we conserve it, that usually means it's 0, but we might actually just keep track of how it changes through time. The conservation of does not mean that it's not changing, it just means we need to keep track of how it changes. Is going to be equal to the amount that comes in, so transport across our surface, whatever our surface is, plus production. And production could be positive if we're actually producing something, or it could be negative if we're getting rid of something. So this is where your question about the sand comes in. In our layered box, if we made the assumption that phi, which in this case is the water, the same amount goes in as comes out, we have our box, we're transporting a certain amount across this boundary, we transport another amount across that boundary. If the water stayed within the sand, then we would have some negative amount of production that is a loss in the system. And we would just keep track of that. But in that particular system, we were assuming that we weren't losing any of the water to the sand. So what this ends up looking like in terms of just a little more equations, we have some kind of a body. So this is x1, x2, x3, and this is our volume. And any surface has a normal to that surface that's going to be perpendicular right at that point, even if it's not a nicely shaped boundary. We usually, capital S is usually the definition of that whole surface. And then at that same point where N is, you might have a Q flux across that boundary. The Q may not be in the same direction as the normal to that surface. So the Q in this sense is kind of like the traction vector of stress. You have a surface, you know, the normal to it, and the traction vector is not necessarily normal to it. So Q, if Q is the transfer of stress across that boundary, then the traction vector would be the parallel to that Q. So we can conserve momentum in that case. But if this is our body of phi, then the volume integral of our v, of phi, is the total amount of phi within there, right? So we're integrating over the whole volume, which is really a triple integral in dx1, dx2, dx3. So that's the volume integral. And that's just saying let's add up all phi within our volume. That's what we start with. What we want to know is, well, how does that total change through time? And how that changes through time happens through K, which is, we often, at least I use, for production of phi. So if we have some way to spontaneously create phi or destroy phi within our volume, then that's what this takes care of. And then there's the surface integral of how much new phi is coming across the boundary, or how much are we losing through that boundary.
Good idea.
So right now it's just sitting there and it's not changing through time. If we were to pull out a Kleenex because we have a runny nose, that would be a certain amount of Kleenexes going through our surface. And in that case, this is changing, but it's only changing due to transport across the surface. We aren't spontaneously creating new Kleenexes inside.
Or destroying Kleenex.
Or destroying Kleenexes, right? So these concepts, just having the amount of change within our volume is due to production of something and transport of something. This applies to all conservation laws. So you can think about phi as energy. You can think of phi as momentum, which is the mass times the velocity it's moving at. You can think of phi as mass. You can think of phi as the number of kids on a school bus. Or as the density of kids. You can think of phi as the amount of salt in a lake, for example. You can think of phi as the pollutants in the atmosphere. So anything that you want to keep track of, you're conserving that. These are the basic inputs and outputs. And you just have to, for that particular situation, define what you mean or what it really means to have like stress transported across a surface versus stress being generated within a body. Do you guys remember the difference between body stresses and surface stress that we talked about early on? For body forces and surface forces. What's a good body force? Gravity, right. What's a good surface force?
Pushing an object.
Yeah. So in that case, production, we produce stress inside a body by putting it into a gravitational environment. So it's produced within the body. It's not transported across the surface in that case. Whereas us pushing on it is transporting that stress across the surface. So when we get to the conservation of momentum, we will be thinking about gravity as being a production of momentum, and other stresses as being ways to transport momentum across the surface. But the specific thing, I think I can get through this one more step in the general conservation law. In that case, we were really fixing our boundary and just thinking about, like, say we have a known boundary. I'm not necessarily saying that it's fixed in space, but it's a known boundary. Say a balloon. A balloon has a certain number of molecules inside it. It might change its density through time by expanding or contracting. If you as we blow into it, we're transporting across the boundary. So you can change your volume you can change the shape of your body without necessarily losing, depending on what it is you're conserving, you can change the shape without it. But it is a fixed boundary in that sense. We're watching this fixed boundary. We're almost inside that volume with it, and we're keeping track of it. It's inside that volume. That's one way to think about it. So if we're sitting on the school bus, we're on the school bus with the kids. We have a little piece of paper. We're keeping track of how many kids get on the bus, how many kids get off of the bus. Our whole world view is just the inside of that bus. And we can write the number of kids through time is a function of the transport of kids across the boundary at each of the stops that we make. Hopefully we're not producing or destroying children.
Plus the number of kids
bus.
born in the bus.
But that's one way that we can look at this as a worldview. The other worldview we can have is if instead of being inside the school bus, let me do it this way, we actually are one of the mothers, or a father who's very observant and sits on their front stoop watching multiple school buses go by, and say the first school bus has 25 kids, another one has 15 kids, and another one has 5 kids, and maybe there's one back here that's got 0 kids in it.
-5.
All we can see is this, right? We're sitting there and this is the only thing we can see. So when we think about the change in that, the change in kids through time, so change in kids through time within our visual box that's stationary now, this actually is a function of the school buses moving. So if the school buses move faster or slower, and if the number of kids in each of the school buses was different, then we would be making different observations. So this is a different way of, basically we can say that the change in phi through time here is actually related to this d phi dx, which is the spatial difference times the velocity at which these buses are moving. Do you see that?
So in this case, we're not just talking about the change of kids on one bus. It's like this bus comes, then this bus comes, and it's different amount of kids. Even though the buses are different, we're still...
So the kids in any particular bus are, through time, are staying the same. It's just us that are observing them changing only because of this lateral movement within the system. So we could also have, say, the middle school bus is the one that her kids get on. So then this bus, by the time it goes through her system, might actually go up to 17, say. So this is a different type of, this actually is a change through time of d phi dt. That's a direct change in time of the amount of kids within her vision. But this effect is not due to a change in time, it's due to a change in space that's happening. And so this actually is what, do you guys remember, what the material derivative is, or the Lagrangian derivative is from other classes? So the total then of both of these is just her kids getting on the bus, which she makes a change at one time, plus the velocity of the buses times the change in kids with space that are on all of the buses.
Then airplane mode should take care of that. Just turn on Wi-Fi and Bluetooth.
It did just say resume recording, so maybe it stayed there. Okay. Anyway, we need to go anyway. Hopefully looks like it might have saved something. So this is a really important property. This material derivative, you have to know which situations. The first case where we're sitting on the school bus, we were pretty much always just dealing with this.
So that's production.
Sorry?
So that's production?
Well, this is the local time change, the actual time change of the volume. This is just the material derivative now. This isn't the whole conservation mess. These both can appear like changes in time. This is the thing, like you won't necessarily know. There's the direct change of what's happening through time, and then there's what looks like it's changing through time, but it only looks like it's changing through time because it's really changing through space. So this is another example would be if you're looking at a river, and it looks like the river is the same, it's always flowing the same, but then without you knowing about it, there's a rainstorm upstream, suddenly the river gets bigger. That's a change through time. a real change through time, but you could also have the river changing through space if you look at that it's always increasing within your field of view. So it's always going from a slow, eddy area to a faster area. You might have a change that's kind of space, even if it's not changing through time. So it's a little bit of a tricky concept to visualize under certain situations, but this is the material derivative, the Lagrangian derivative, and we'll come back to it because it depends whether you use it depends on your perspective in the problem and how you draw your boundaries. But then that general conservation law always has a production term, it always has a